This is Algebra 2, Chapter 7, Section 6, in which we will study common logarithms. And the common logarithm is just a log with a base of 10. And we use base 10 because we have 10 fingers. If we were creatures like Yoda, then we would be counting in base 6, and so base 6 would be our common log. But base 10 because we're us. Typically, when you write the common log, you don't write it with the base on it. It's understood to be 10 unless they tell you otherwise. Now, on your calculator, you should see a button that says log. It may be hidden inside a menu. If you don't find your log button, make sure you ask me in class. I'll help you find where it is. Sometimes they do like to hide them. But this log button calculates the common log of some value. So with your trusty calculator, make sure you can use it properly. Let's calculate the log of 7. So I push log of 7 on my calculator, and I get the answer of 0.845. There's more to it, but of course we like to round. Log of 0.5, I get negative 0.301. If you had trouble finding those answers, if you couldn't get those answers out of your calculator, make sure you ask me and I'll help you out. Some calculators take the 7 and then the log. Some take log and then 7 and then an equal sign or an enter or something like that. So it kind of varies by calculator, but I'll be more than happy to show you if you had trouble getting to those answers. All you have to do is ask. Now, we use common logs in a few applications. They're used, the examples we're going to be working with are sound measurements. It's also used in chemistry to find pH, how acidic or how basic something is. And it's also used as part of the Richter scale measurement for earthquake intensities. But we're going to work with it just in terms of sound here. And our formula is L equals 10 times log of I. Okay. L stands for the loudness of the sound measured in decibels. And I stands for the sound intensity, which is the number of times it is more intense than the softest minimum audible sound. There's a certain sound level that it takes for humans to hear. And we use that as our basis. And you'll see how that works here in just a minute. So suppose they tell you that there's a noise that its loudness level is 82 decibels. Okay, we're going to use our magic formula, L equals 10 log I. We know what L is 82. Divide by 10, we get log I equals 8.2. Now, to get rid of the log, we need to do the inverse log on our calculator. That will be a second log or a shift log or something like that. And if you inverse log 8.2, you get this crazy answer, like 158 million and change. Okay, time we do a little rounding to make it where we don't have to write so much. We're going to find out that the loudness level, the intensity level, is 160 million times the softest sound you can hear. And that's just 82 decibels. Okay, something like a jet engine running or a rock concert, those are upwards of 120 decibels. 80 decibels isn't really all that loud. I mean, it's loud enough that you'll notice it, but it's not overly loud. Just to give you a little background there. Okay, another kind of problem they're going to throw at us looks like an old friend of ours. They're going to give us something with an exponential equal to another value. But the trick is, we can't make 15 into a power of 3. like we could on the previous ones that we did earlier in the chapter. When you can't make it match up, then we're not going to be able to cancel the bases, so the next trick is to take a log of both sides. So I'm going to take log of both sides of the equation. Now I'm going to use the property we learned in the last section and drop that x down in front. Log of 3, my calculator tells me, is 0.477. Log of 15, it tells me, is 1.176. Now I can solve for x just by dividing. Okay. Let's go through another one of that nature. We have 6 to the something equals 42. Well, we're not able to make that into a power of 6, so we're going to need to take a log. We'll use that property of logs again to drop the x down in front. Go to our trusty calculator to get a couple of numbers for the logs, and then divide it out. Okay. Those aren't so bad. There's another kind of problem that looks more intimidating than it is. And they throw at you log base 4 of 12. And it looks like it would be kind of a scary problem. But it's not so bad if you remember the trick we used on the previous days, where we put an equals x on the end. Now if we have an equals x on the end, we know what to do because we can flip-flop it. 4 to the x equals 12. Now it's a problem like we just did on the previous page. Take the log, and I'm going to go ahead and move the x down as I go. Use our calculator and divide. Okay. Not really all that tricky. The only difference is you have to remember to do the flip-flop step first. One last problem for this section. It's the same idea, but they throw an inequality at us. Well, that's okay. We can handle that. The same basic plan still applies. We're going to take logs. So we take a log of both sides. Then we'll use the exponent rule, drop the 2x down, and drop the x plus 1 down. And I'm going to be careful and put that in parentheses so I remember it's the whole thing being multiplied by the log of 6. Trusty calculator gives me some values for log of 3 and log of 6. Distribute and collect up things, clean them up. Subtract the x's over. And presto, when we divide, we get our final answer. So common logs, not so bad. They help us with problems where we can't get the bases alike. And it's just the regular log button on our calculator, which is all well and good. So we get to do a lot of calculator work to get to some numerical answers. We're going to get a lot of decimals, but that's okay. We're not scared. And as always, if you had questions along the way, hopefully you wrote those down. Bring them in, and we will see you in class.